Yeah, I'll let you know once we are live. Yeah, go ahead, Suhail.
Okay. Welcome everybody to the second session in the first day of the coding theory course. I'm Suhail Sherif, and this tutorial is going to be about a hat puzzle by a person named Todd Ebert, who had included it in his PhD thesis. Now, I don't think there's anything that I can say that will get your attention more than this is about a puzzle. So let's just dive right into the puzzle. Some of you might have seen a depiction of the puzzle, something that looks like this. It's not inaccurate, but let's see something that's a bit more descriptive. So this image I've taken from the thumbnail of a video on YouTube. That video is also about a hat problem, but it's a slightly different hat problem than this one. It's also interesting. But the depiction is quite similar. So there are 7 people, as you can see here. If this works. Yeah, okay. Right, so there are 7 people. Each of them are wearing hats. And in this thumbnail, the hat is either blue or pink. In our talk, it's going to be black or white, but let's just look at this thumbnail and think that it's blue or pink for now. So in this thumbnail, we're seeing this scenario from the setting of player number 3. And player number 3 doesn't know which hat they have on their head, which is why it's colorless in this picture. But they can see the colors of all the other hats. And this Mad Hatter on the bottom right is asking player 3 whether their hat is blue or pink. Obviously, player 3 doesn't really know what their hat color is, so they can't really answer it with certainty. So what is this puzzle about? Obviously, you can't answer it with certainty, so how do you want to answer it? So the formal setting, I'll show you now. The beginning part we've already seen. 7 people are going to participate in this activity, which is being kidnapped, I guess. And a hat is going to be placed on each of their heads, and it's either a white hat or a black hat. Each player can only see the hats of other players. They can't see their own hats, and they're not allowed to communicate. Once the activity starts, they're not allowed to communicate. They can come up with strategies beforehand, before the activity starts, before they can see the hats of the other players. But once the activity starts, they're not allowed to communicate. And what they want to do is this. They're given one of 3 possible actions. Either they guess that their hat is white, or they guess that their hat is black, or they pass. So each one will be asked to do one of these actions. And when they're guessing the color of their hat, they're guessing it silently. They're probably writing it on a sheet of paper and handing it to the Mad Hatter. Other people don't get to know what this person has guessed. So they're all guessing simultaneously without knowing each other's answers. Of course, they have an option to pass. And when do we say that these 7 people have actually, let's say, won at this activity? The group wins if the number of correct guesses is greater than 0. That's at least one person has to guess correctly. And the number of wrong guesses is equal to 0. So if even one person guesses wrong, then the whole team loses. If there are some people who guess correct and one person wrong, again, the whole team loses. If some people guess correct, the other people pass, then the team wins. If everybody passes, again, the team loses. All right, so this is the setup. And the rest of the talk is going to just be analyzing this simple setup. So if there are any doubts, any clarifications one wants to make, this would be a good time to make them.
Are they sitting in a particular order, like in a circle or in a straight line or something?
So you can assume that they're sitting in a circle. Basically, everybody knows everybody else. So you can tell that player number 1 is wearing a pink hat, player number 2 is wearing a blue hat. So yeah, all the information. This is all the information that the player gets.
So
They
does everybody guess at the same time?
Sorry?
Everybody guesses at the same time.
Everybody guesses at the same time, yes.
You know, number of black or white hats.
They don't know the number of black or white hats. It can be anything. It can be all black or white. So I guess I'll go ahead then. So yeah, what is our goal? So we're going to see pretty soon that we can't actually win this all the time. We're going to have to lose some of the cases. So what we want to do is we just want to come up with a strategy that does well. And what do we mean by does well? Let's see how many cases we have. So what is this question? How well does your strategy do? So there are many cases that it could have been. So let's just write down an example case. It could be, say, black, white, black, black, white, white, white. Say. So this means player 1 has a black hat, player 2 has a white hat, player 3 has a black hat, and so on. And if this is in this setting, we'll see what each player guesses. So we'll have one action from player 1, action 1, action 2, up till action 7. And given all these actions and their hat colors, we can find out whether they won or lost. And how many possible settings of this are there? Can anybody quickly calculate that? This is just one of the possible settings.
2 to the power 7.
Yes, so there are exactly 2 to the power 7 settings. And when we want to evaluate how well a strategy does, what we're going to be asking is, how many of these 2 to the power 7 settings do you actually win? So we want a strategy that maximizes the number of one settings. Right. Okay. So by now we've actually completely finished formally defining the problem, or at least we've defined it in enough detail that it can be written formally. So let's actually do a little bit of formal writing here. What I want to know now is, what is a strategy? Okay. And can anyone give an example of, say, what is an example player 1 strategy? So we'll write player 1 strategy as S1. So S1 could be something as simple as look at player 2's hat and guess that color. Or it could actually be even simpler. It can just be pass all the time. Just always pass is a valid strategy. So how do I actually write down the set of all possible strategies of player 1? Does anyone have an idea of how you can go about specifying a strategy? Also, it's a tutorial. It's going to be mostly interactive. If you want to just keep yourself unmuted throughout and have a conversation as we go through the slides, conversation with me, not with like somebody else, that's fine.
So maybe the player 1 first decides which other player should he guess, which other player's hat should he guess,
Right. So
and then maybe which color can he guess. So I think these two things are something that he will think about.
right. So yeah, exactly. So what all can he think about? He can think about which player's hats he should look at, and based on the player's hats, which colors should he guess, right? So
the ith place strategy is function from in 6 bits to one bit.
So the strategy can be specified completely by looking at what input the strategy gets. So S1 is actually a function. It's a function that takes as input the other player's hats. So we'll write that as black and white to the power 6. So this means a length 6 string of black and white. So for example, this could be something like, if this is the string, this is supposed to be its input is basically that player 2 has black, player 3 has black, player 4 has white, player 5 has white, and player 6 and 7 have black. And its output is one of let's see, guess black, or guess white, or pass. Right? So this is a completely formal description of a strategy. Any strategy you can think of, as long as it's deterministic, will be of this form. And we'll only be considering deterministic strategies in this talk. We won't give them access to randomness, but whatever we learn from deterministic will easily translate to the randomized setting as well. All right. So this is good. So each, in fact, not just S1, but for every player, every I from 1 to 7, SI is just a function. And its input is 6 hat colors, and output is guess black, guess white for us. Okay. So let's look at an example strategy. So suppose S1's strategy. So S1 is actually somebody who really likes black hats. Very understandable. Black hats are very classy. So S1 just always outputs guess black. Right. So can anyone tell me how many of these cases will S1 be correct in, and how many of these cases will S1 be wrong in?
2 by 3 chances that S1 will be right.
Sorry?
2 by 3 chances are there that S1 will be right
Why is it 2 by 3?
based on the probability. As the others, 4 people have black caps.
So we don't actually know how many black hats are there and how many white hats are there. So in these 128 cases,
You said that one person can see others' hats.
yes, that's true. But suppose player 1 sees all the hats are black. All the hats that player 1 sees are black. So then,
No, I think the confusion is that the above example, BB, that's just one instance,
right.
but let's ignore that. Maybe that's
Okay.
If the first player always outputs the black, that
Yeah.
means 1/3 of the time he'll be right.
why?
Because when the hat on his head is black, he's correct.
Yes.
In other cases, he is wrong.
Yes.
Unless he passes, but it's given that he always outputs a black. So it should be 1/3, I think.
No, so he always passes. He never passes. So there are only two cases to consider. Either his hat is black or his hat is white.
Oh, then 1/2.
1 by 2.
Right, exactly. So 64 out of these 128 cases, player 1 gets a black hat. And in 64 out of 128 cases, player 1 will get a white hat. Because each case is equally likely. So half the time he'll get black, half the time he'll get white. And so if he always outputs GB, this is 64 correct guesses out of the 128 guesses that he can possibly face, and 64 wrong. So notice that if you're playing as a team, and you know that S1 is always going to output black, you already know that 64 of your settings you've already lost, because if you have even one wrong answer, you've lost the case. Okay. So I'm going to make a claim here that if I know that S1 is always outputting black, my best option is to just pass, is to always pass. Right? Because 64 of the cases are doomed, they're wrong. In 64 cases, he's correct. And if nobody else passes, then we actually win all those 64 cases. Because
Nobody else guesses it wrong.
Yeah, nobody else guesses it wrong because you've passed. So if one person is always outputting a color, then it's just best to pass. If you want to do better than half, if that's even possible, then it's important that everybody should be passing at least some of the time. If one person is never passing, then you've already doomed yourself to getting at most half of the cases correct. Right? I'm putting up a poll just to see. Yeah. At least the logic that we followed till here, is it? And what is it? Clear, really big.
Sir, but if S1 turns out to be wrong, won't they like lose the game automatically?
Yes, so if S1 is wrong, they've already lost the game. So in those cases, that happens in 64 of the cases. And those 64 cases they've lost. But maybe in the cases where they're right, they don't have to lose any more cases.
Sir,
Well, see, this is a probabilistic strategy, like there's no exact strategy we'll guess.
Sorry, which is a probabilistic strategy?
This is like this, it's not a strategy which ensures winning.
Yes, it's not a strategy that ensures winning. It just says that half the time it's going to lose, half
Like
the time it's going to
they just want to maximize their chances of winning.
Yeah, exactly. We'll see soon that you can't win all the time.
sir, if you said that all the people must output together, so how? So that means S1, like the strategies of all the others are known beforehand. So those are also inputs to.
That's true. So I'm saying that suppose you have one stubborn person in your group who is saying they're always going to guess black. Then the rest of the team, it's better if the rest of the team passes. This is something they'll decide beforehand. That if S1 is actually going to be so stubborn, then we should all pass. Of course, it's better if S1 can cooperate with the rest, and hopefully they can do better if they cooperate. So this is if this strategy has S1 always outputs.
What's the use of this thing? I mean, if even if others do not pass the question, the answer, then too there are half and half chances of winning or losing.
Exactly. That is a very good point, which is exactly our next slide. And I think you'll relate very much with the title of the slide. So what are they even trying to do? None of them know what their hat is, and they want to guess. Why are they even trying? Why not just give up and say whatever you want? Well, there's some point to trying. For instance, if everybody actually gave up and said whatever they want, suppose S1 always outputs GB, and S2 also always outputs GB, then the number of correct, they would have lost more than half. They would have lost 3/4 of the settings immediately. Because S1 will lose half of the cases. And then in the times when S1 is correct, S2 will get half of those wrong. So this is something that you can calculate. But there is some amount of planning that you can do to not do too bad. And that we're going to try to analyze this a bit more mathematically now to see exactly what is it that they can do, even though they're a bunch of idiots.
So can they do better than us?
That is what we are coming to.
Okay.
So I have a question.
Yeah.
So what if S1 knows everyone else is going to pass and he just decides, or she decides to just toss a coin?
So if S1 also passes, knowing that everyone else is passing, then
No, S1 just decides to toss a coin and say.
to toss a coin, I say. So that would be a randomized strategy, and it is a very valid strategy that we should look at. But I don't think we'll have time to look at such randomized strategies in this talk. So that's why. So in that setting, SI would not be a function like this.
Okay.
Based on its input, then its output would also be randomized with
Okay.
GB with probability half, GW with probability half. We won't look at that this talk.
Okay.
But maybe at the end of the talk, if there's time, I can tell you about what happens in those cases.
Okay.
Nice question. Okay. So this is exactly what we have come to. None of them know anything about their hat color. What are the consequences of them not knowing anything about their hat color? And I'm going to put up a poll. You can take your time with this poll. Is the poll up? Or relaunched? Yeah, okay, so you should have a poll up right now. Yeah, just think about each of these. You can take your time. The fact that each player doesn't know what their hat color is, what does this mean for the scenario? So multiple of these can be correct. We have to find out which of these are correct and which of these you don't really see, or which of these are wrong. Don't choose the ones that are wrong, or don't choose the ones that you don't immediately see. Whatever you immediately see as a consequence, choose this. In fact, I will actually go and get myself some water, so you do have time to just.
I mean, in the meantime, if maybe there are any clarifications that people want, then one of us can help with that. Actually, maybe I should have set up a poll as to what people think is how often do people think we can get right? And we saw a strategy that gets right 50% of the time. Are there people here who believe that we can do better than 50%?
Raise hands if you think that.
Yeah.
So nobody thinks it can be better.
This is like the best case scenario.
Yeah.
Yeah.
Yeah, so everybody disagrees with the title of the slide in that case.
What happened?
Well, I was just asking if how many people here believe that we can do better than 50%. So, and at the moment, it feels like nobody thinks we can do better than 50%. So, Rishona does. Or is that right? Or was that a question?
Yeah, I think we can do better than.
Yes. Good. Okay. We'll see. We'll see whether that is indeed true or.
Okay. I think I'll end the poll. So most people got, and the most common answer that was chosen is the first answer. And the first answer is actually correct. So each player is going to answer in the 128 different settings. And the player might pass some of the times, but among the times that it doesn't pass, it'll get equal number of right guesses and wrong guesses. So let's just see this fact. So suppose you're looking at player one, right? So looking at player one, and you're seeing what did they do on some input case. Let's just put a random case here. Black, white, white, black, white, white. In this case, player one probably, so let's say they guessed black. So here player one is only seeing the hats of the other players. So there are two possibilities for what the actual case can be. It can either be player one had white, and then the rest of this is the same as above. Same as that. I hope that's clear. Or the case can be that it was player one's hat was black and everything else was the same. These are the only two cases compatible with what player one is seeing. And since they guessed black, they're wrong in one of the cases and they're right in one of the cases. Similarly, if they had guessed white, they would have been wrong in one of the cases and right in one of the cases. If they had just passed, they would have, not been wrong or right in both cases. So you can just go through each of the possible inputs that player one gets. And for every time they actually guess something, that's one wrong guess and one right guess. So the number of total guesses that player one makes that are right is equal to the number of guesses that they make that are wrong. So that's option one was correct. As a consequence of option one, option four will also be correct. That is that there are 7 players. And if you look at all of their answers, the 128 into 7 answers that they have, each player has the equal number of right and wrong guesses. So overall also, they will have an equal number of right guesses and wrong guesses. Is that clear? Anybody? So I will. So the silence means that it's not clear. Okay, so I'll just repeat what I said. So let's look at an easier case where, suppose there were only 3 players. Let's see how. You have very few cases. So you have black, 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 white, black, white, black. What else? White, black, black. And then you have some you have 4 more cases like this. But let's just look at, suppose S1 saw black and black. So that means that we're either in this case or we're in this case. And if S1 guesses black, then they're correct in this case and they're wrong in this case. And suppose S1 saw black and white, that means it's either this case or it's white, black, white. In this case, S1, if they guess something, it would be wrong in one of the cases and right in one of the cases. So if you look through this and see, I mean, right now what we've seen is that 2 of S1's guesses are wrong and 2 of S1's guesses are right. And this will continue as we look at all the cases. Similarly, we can look at S2. So if you're looking at S2 of, let's say, black and black, that means that, okay, this is a different color. So that means that either they're in this case or they're in this case, because S1 should be black, S3 should be black. Again, if they guess, they'll be wrong in one of the cases, they'll be right in one of the cases. And so you can see that the number of right tick marks that I make in this whole setting has to be equal to the number of wrong tick marks that I make. And this implies both that each player has an equal number of right and wrong guesses, and that as a whole, the group has an equal number of right and wrong guesses. But this doesn't yet mean that the number of cases that they win is equal to the number of cases that they lose. That is not yet implied, at least not with such simple logic. Okay. I realize that this might not have been the clearest explanation, but in case there was anyone confused and this helped, that would be worth it. Okay. So I'll just move on. Hopefully some parts will become clear as we see the rest. Okay, what were the other options actually? The other options in the poll. Oh, actually, there are lots of chat. Oh.
No, so so Janaki pointed out that basically if we had just one player instead of 7 or whatever, we can't do better than 50%.
Right.
That is true. And there's some thought about, if we have more players, will it get worse? I was just pointing out that, like with more players, you can always ask a few players to always pass and pretend to work like a.
Sir, I have a doubt. Like when you're saying we can pass it, so say on the first round, if nobody's sure of what their guess should be and they don't want to get wrong guesses, if everyone passes, how will that enable other people to make a correct guess?
So there are no rounds in this. Everyone's guessing simultaneously.
Okay.
So
But
if you pass, then you've just
pass.
passed. If everyone passes, then they've lost the case.
Okay.
If some players pass, then they're kind of worthless. I mean, it's like they weren't even playing in the game. So it really depends on what the other people guess.
Right. Okay.
So,
but if their answers are independent of each other, then how can the probability of getting it correct exceed 50%? Because they are completely independent.
So their inputs are independent of each other. Which hat I have is independent of which hat you have. But with a strategy, you can actually make them not independent of each other anymore. So the answers need not actually be independent of each other, even though their inputs are independent of each other. And we'll see a case pretty soon. We'll actually see. I mean, we're going to go through the actual optimal answer. So hopefully it should get clear. Okay, so now, okay, we have these nice statements about the number of correct and wrong guesses, and we're going to use these statements now. So I'm going to claim that they cannot win all 128 cases. And this logic is going to be pretty simple. If they've won all 128 cases, that means that in each of the case, somebody has guessed correctly. Right? Because that's the only way you can win is if somebody has to guess correctly to win. But if somebody has guessed correctly in one case, we just saw that they have to guess wrong in some other case. Each player has an equal number of right and wrong guesses. So if they've guessed wrong in some other case, they've automatically lost that case. So it's impossible to win all 128 cases. That at least, it's not much of a statement. I don't think anyone is surprised by the statement, but it's very useful that we can formally prove this statement, because you have to have a correct guess to win, and therefore you have to have a wrong guess, and therefore you cannot win all 128 cases. But how about this? So I'm going to tell you that I have a strategy which won at least 50 cases it has won. So that means at least 50 cases have a correct guess. Somebody has guessed correctly in at least 50 of the cases. My question is, how many cases must they have lost because of wrong guesses? And I would, this would be useful to have someone to discuss with. So if anyone even from the organizers are fine with discussing it.
By the way, I thought maybe I'll just let people know in case, I don't know if everybody is following the chat. So Arpita just mentioned that with the 3 people setting, you could have a strategy that does better than half. So she just outlined a strategy in the chat. It's an excellent, it's excellent starting point. Yeah.
Right. So in Arpita's chat, everybody is using the same strategy, which is looking at the other 2 people's hats. There are only 3 people. And if the other 2 hats are the same color, if the other 2 hats are different colors, then you pass. If the other 2 hats are the same color, then you guess the same color as well.
So you guess the other color. Oh, sorry. So she just, okay. So, yeah. Okay. Okay, no, so sorry, I misread what Arpita was suggesting. Slightly off. Yeah.
So actually, it's not for all. Only like one of them will do this, and the rest 2 will have different strategies. Like,
I see.
I'm not very sure, but
yeah, but there is something very similar to this, looking very similar, and it was enough to fool Arpita. So.
Actually, in real life, I think these type of strategies will not work, because in general, this is the case that when other 2 are black, then there are possibilities of that the third one will be white something.
Right. Yeah. So it won't work all the time, but it surprisingly does. Something that doesn't seem like it should work does work, and we'll see why. You're right. Even I would be surprised when somebody tells me the strategy that works until I actually calculate it, and then I can't argue with maths. But until the maths actually makes its argument, I would also be doubtful. Okay, so let's answer this question. So at least 50 cases have been won. Right? So that means that there have been at least 50 correct guesses by, I mean, it need not be by one player. It could be by multiple players across cases. But what we know is that there are at least 50 cases that have been won. So there are at least 50 tick marks in this kind of diagram that I've drawn here. There would be at least 50 tick marks. So what we saw from the previous slide was that this implies that there are also at least 50 cross marks. We just went through that argument earlier. But if there are at least 50 cross marks, how many cases can you guarantee have been lost? So the question is basically, there are at least 50 cross marks. We know this to be true. This implies at least dash lost cases. So what is the correct answer to go in that dash? Did somebody say something? Sorry. It's fine if you don't get the answer, as long as you're thinking about it.
So at least 50 are wrong. That implies at least a certain number lost cases. Lost cases meaning wrong, including all passes, like everyone passes, or
Oh no, just because of wrong guesses. Sorry?
Tanya, somehow your voice is very low. We are not able to hear you.
Then this would be 50, I think.
So suppose somebody loses a case. Suppose there's a case which is, let's say, this case. I don't know why I keep on choosing this one. Suppose player one guesses white. So player one is wrong here.
By the way, there's 6 of them here, but
Oh, good. So player one guesses white and is wrong. Player two guesses white and is wrong. Maybe player three guesses white and is correct. Player four guesses white and is wrong. I don't know. Everyone's guessing white. But sure, let's just do that. Everyone's guessing white for some reason.
Even if it's first give wrong answer, then 2 it will pass.
Sorry?
Even if the first one gives wrong answer, then 2 it will pass. Means the next one will also answer the same, and next one will also answer.
So
I thought if the first one is wrong, then okay, we have lost.
But we don't know if we don't know what the first person has guessed. Everyone's guessing simultaneously. So what I said earlier was that if the strategy of player one is to always guess white, then everyone else should pass. Here, I'm not saying that the strategy of player one is to always guess white. The strategy of player one could have been anything. Let's suppose that in this specific case, they guess white.
At least 8 lost cases would be there then.
Exactly, yes. Because each of the cases, I mean, you can have 7 wrong answers all in the same case. And that's a good thing for us, actually, because we have at least 50 crosses. And by making all the crosses go into the same cases, we're actually using very few lost cases to cover all those 50 crosses. So, yeah. So the answer is there are at least 8 cases because of wrong guesses. So this is the first point where you see that, okay, maybe they can do better than half because they've won 50 cases, but lost only 8 cases. That's still a possibility for us. And this is what we want to get to. We want to get to strategies that end up looking like this. Right? So in fact, if you've won at least, say, give me a good variable. If you won at least a number of cases, then you must have lost at least a divided by 7 cases just because of wrong guesses.
And it may turn to 0 also because in the question it's not mentioned that at least 50 right implies at least 50 wrong.
But this is what we saw from the previous slide. In the previous slide, we saw that if there are 50 from the poll, actually, I'll just.
We said if there are 50 right answer and then others may pass also.
No, but so in this poll, I'm just relaunching it now so that you can see it. So we said that the first answer was correct. Among all the answers that each player gives, there are an equal number of right guesses and wrong guesses. And we said that the fourth answer was correct. Among all the answers of all the players, there are an equal number of right guesses and wrong guesses. So just because of that, if you have 150 cases, that means you must have made at least 50 right guesses. And that means you have made at least 50 wrong guesses. So that's why I wrote that implies at the bottom left. This we've actually proved already. So now we can ask, what is the maximum number that they can possibly win? So we know that if you've won A cases, this implies that you've lost A by 7 cases. So overall, there are 128 cases. So let's see what the maximum number that you can win is. That would be a plus a by 7 is equal to 128. And then you do some magic and you get a equal to 128 divided by 8 into 7.
So this is 112.
Equal 16. Yeah. So 112. So if they win 112 cases, then they will lose 16 cases, and that covers 128 cases. If they've won 113 cases, then they've lost at least 17 cases, which is not possible because that's just too many cases. You don't have that many cases. So it's impossible to win more than 112. We don't know if it's possible to win 112 yet. All that we know is that if anything, it's at most 112. And this is the crux of the solution to the puzzle. If it's possible to win 112 cases, what would it look like? So you can probably list down all the cases, case number 1, case number 2, and so on to case number 128. And so you can ask how many correct guesses and wrong guesses were made in case number 1. So for it to actually be 112 cases, it should look something like this. In most of the cases, you have exactly one correct answer. In fact, up till case 112, you have one correct answer. And from 113 onwards, every case has 7 wrong answers. Sorry?
We are not able to hear you, Tanya. Can you?
Sorry. I was saying that it must be 1 wrong in 113 case and 7 wrong in all the other cases.
Why 1 wrong in 113 case?
I think we did something like it was 50 and there were 50 wrong cases and we had to divide it with 7.
Right, so that was the case when you had 50 cases correct, when you had 50 correct guesses. But now we're looking at 112 correct guesses. So if you look at 112 correct guesses, then if you divide by 7, you actually get exactly 16.
Yeah. Thank you.
So we want a strategy that somehow looks like this. In many of the cases, it has exactly 1 correct. And in other cases, it has 7 wrong answers, like everybody's wrong. And in order to find a strategy that looks like this, we'll actually focus on the wrong cases. What we're going to do is we're going to look for a strategy and we're going to pick a specific case and we're going to try to, and we're going to look at a specific case and we're going to try to make everybody wrong on that specific case. It looks weird, like this looks like you're trying to come up with the worst strategy ever. But by our logic here, this is what the best strategy should look like. So let's actually look at a case here. So I'm going to end up with the same case if I write it. Let me start with W dot B. Okay. So let's focus on this one case. And I want everybody to get this one case wrong. So what can you tell me about their strategies if they have to get this case wrong? Let's not come up with the full strategy yet, but let's slowly build up the strategy in order to get this one case wrong by everybody. So can somebody tell me what the strategy needs to look like? Third person? Again, your voice is very faint.
Like they may guess like who is sitting third to them, and they may say that the same color would be of their cap.
Right.
Because in this case, they'll guess black.
That would work. In this case, everybody gets it wrong. So what you're saying is, but the reason you said this was because you wanted player 1. When the player 1 sees WW BW, they should guess black. Right? That's why you said look at the third hat, because you wanted this to be true.
Yes.
And similarly, if you look at, say, the fourth person, you want, if they see WWW, BBW, you want them to guess white.
Yes.
And so on. So let's just stick to this for now. Let's not decide what they should do always. Let's just decide what they do in these cases, so that all of them get this wrong.
But aren't they sitting in a circle you mentioned earlier?
Sure, they could be sitting in a circle.
The strategy here is not guessing what the color is, let's say 3 hats down the line, but just that if this is the sequence they see, then they guess black. I mean, the first player, when the sequence the first player sees is WWB, BBW, then they guess black. And similarly for each of the other things.
So what we've done is we've decided what they should guess in one particular setting. We've guessed this for all 7 players. So in this case, S1, as we've designed it, S1 will get this wrong, S2 will get this wrong, S3 will get this wrong. Everybody gets this wrong. And that's a good thing for us, because the optimal strategy should look something like this. But the fact that they've guessed these wrong actually means that they've guessed some other things correctly, because you have to have an equal number of correct and wrong guesses, right? So can somebody tell me what is a correct guess that would happen because of these because of this strategy? So let's say in which case does player 1 guess correctly? There is one case in which player 1 has to guess correctly because he's guessed wrong over here. So just with what we know about his strategies so far, which case does player 1 guess correctly?
If there is black.
Yes. 2 people can speak. I'll try to understand. So I heard if there is black, and that is the correct start to the sentence. So if it's black, white, white, black, 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 white, then in this case, player 1 guesses correctly. Notice that in this case, player 2 doesn't, let's at least look at player 4. What player 4 sees is black, white, white, black, black, white, which isn't the same as what we've made the strategy for. So in this case, player 4 actually doesn't guess anything yet. So player 4's is currently unspecified. And even player 2's guess is unspecified. Everybody's guess over here is unspecified. We haven't yet, the strategy hasn't yet told them what to guess over here. The strategy has only told player 1 what to guess over here, and that guess is correct. So let's just make some space. So similarly, if you had seen the case white, black, white, black, 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 white, player 2 will guess correctly here, and nobody else will guess in this case. If you see white, white, black, 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 white, then here player 3 will guess correctly, nobody else will guess. And notice that all that we're doing here is we're just flipping one of the hat colors. So this and this just have the first hat color flipped. This and this have the second hat color flipped. This and this have the third hat color flipped. And so on, there would be a fourth, a fifth, a sixth, and a seventh. So as of now, what we've done with our current strategy is we've gotten, in one case, we've gotten 7 wrong answers. And in 7 cases, we've gotten 1 right answer each. And that's exactly the kind of thing we were going for. But the one problem over here is that we've won 7 cases. We've lost 1 case because of wrong answers. And then we've lost 120 other cases because everybody passed. So we shouldn't yet be completely happy. We've mimicked a small part of the optimal strategy, but we still have the rest of the optimal strategy to mimic. Okay, so but this is a good starting point. In fact, it's a great starting point, right?
Even if we are saying that one win means with this strategy, each exactly one person wins in 7 cases.
Yes.
Then two, it's of no worth if one person is winning and 6 other are losing due to this strategy actually.
But 6 others are not losing. 6 others haven't guessed right now. Maybe we'll make them pass. So we'll make all the other people pass in these cases. And so it'll be 1 correct, 6 passes, and the team wins in each of these cases.
That means we shall modify the strategy somehow.
So right now we haven't yet specified, but you're right. What we should say is that we should modify the strategy to make sure that all of these, instead of being unspecified, all of these are actually passes. Okay. If we manage this, then we're happy, because 1 case, 7 wrong answers, 7 cases, 1 correct answer, and 6 passes. So let's see what else we can do to get more things like this. So right now we've touched 8 cases, and there are still 120 cases untouched. Not touched. So now what one would think that they should do is they should do exactly the same thing. They should find another case and try to get that case all wrong, so that you've won 7 more cases and lost 1 more case. Right? So maybe you would think, maybe if the setting is black, black, white, black, 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 white, maybe what you'll try to do is you'll try to make all of these wrong. So that's 1 more case that you've lost. But because you've lost this case with all wrong, you would have won 7 new cases. This is.
I have a question.
Yeah.
Why are we ignoring all the 7 right cases?
Why are we ignoring them?
All the 7 right cases.
No, but what do you mean by ignoring?
Means we are discussing 1 case in which all the 7 are wrong. We are discussing that case.
Because it's easier to make all 7 wrong than to make exactly 1 right. And if you try to think about how you would go about making exactly 1 right.
No, I am asking about the case when all the 7 are right.
All the 7 are right. So what we saw from the previous slide was that if you have a strategy that wins 112 cases, there is no case where all 7 are right.
Okay. We are discussing for this case.
So there are only cases where 1 person is right, and there are cases where 7 people are wrong, and that's it. So that's what we're trying to mimic.
Okay.
So I have colors. Why am I not using colors? So this one was wrong, and all these others are right. This is good. The amount of red is very small compared to the amount of green. Okay, so maybe now we try to do the same thing again. Over here, we'll get 1 all wrong. And then all of its neighbors, we want all those will automatically become correct because this one is wrong, just like it happened above. Okay, so you have 7 neighbors here, 2, 3, 4, 5, 6, 7 neighbors here. And we want all of those to be right. I mean, they will actually all be right. But there's one problem here. If you look at, which case would it be? This one. This case over here, it's actually just flipping the second hat from here. We can use a mouse. Yeah. So it's the second hat has changed over here to get to this case. And if you look at these 2 cases, only the first hat has changed to get to this case. Right? So if you had chosen this second case and made all of these wrong, then in fact, over here, you will have 2 correct and 5 passes instead of 1 correct and 5 passes. We wanted to have one correct because that's what the optimal strategy looks like. And unfortunately, we just chose wrong. This was a wrong choice. We should have chosen some other hat setting. A hat setting which would have left all of these cases in the green box. All of those we want them to stay as is because they already have one correct case. They already have one correct guess each.
It's something like the notion of cosets in linear algebra in quotient mapping.
So you can think of these as cosets. This is a group of, you can think of this as a group and there being cosets here, but that's not, I don't think that's a very useful angle to look at it from here. Oh, you're muted.
Sorry, no, that wasn't me. I don't know what happened. Anyway.
Okay, so is it in progress or not?
No, recording is, I mean, in the sense the live stream is still going on. You may continue. Yeah. By the way, we have about 15 minutes left. Is that right?
We should have.
Yeah.
Yeah, about 15.
Okay, so what was our wrong choice here? We took, and we started off very well. This was a correct thing to do. We took a case, we got all of them wrong, 7 correct. Our next step, we did wrong because we took a case which interfered with our previous cases. So we want a case which doesn't interfere with our previous cases. The second choice, I mean, it is the correct thing to do, to look for some other case and get all of them wrong. But we should do that choosing very smartly. So let's just open a new page where it's not full of already written stuff. Okay, so let's say we took case, let's call this case 1. Okay, and let's say case 1, we made 7 wrong. So this made a bunch of cases, like case 2 until case 8. It made all of these have exactly one correct answer, which was good. And these all are just, they're just changing one hat from case 1. Now we want to choose a new case to have 7 wrong answers, right? So let's call that case 9 has 7 wrong answers. And we want to choose it in such a way that if you look at its neighbors, the 7 things that you can get by flipping a bit, all these should be completely new cases. We shouldn't have seen any of these cases before. Case 10 till case 7, 16. Now, this kind of a structure, this is a very structured problem that we're asking for now. So what we want is that, so this is, let's call these special cases where we're getting it wrong. Let's call them W cases because they're wrong cases. So we want to ensure that when we're choosing our wrong cases, it should not be the case that you can go from one wrong case to another wrong case in 2 steps. If you could go from one wrong case to the other wrong case in 2 steps by flipping one hat, and then by flipping another hat, that means that this middle case over here, this was being touched by the wrong case 1 and being touched by the wrong case 9. So it should never be the case that 2 of your wrong cases are just, let's say, a distance 2 from each other. It's a weird word, distance. I think I've heard the word distance before today. Probably a coincidence. So yeah, now we know what we want. We want all these wrong cases. So let's just make a query to the math gods. Dear math gods, can you please give us a set of wrong cases? Right? So each wrong case is going to be some element of BW to the 7. And we want it to be such that if I take any 2 wrong cases, so wrong case A and wrong case B, the distance from wrong case A to wrong case B should be larger than 2. It should be at least 3. So when the math gods give us, assuming they're going to give us this set S, right? So that means it says K elements here. So that means that we have K wrong cases. They all have distance at least 3 from each other. So that means that for each of these wrong cases, the 7 neighbors of the wrong cases, so for each wrong case, it's 7 neighbors, 7 wrong cases, which means that they're actually here wrong cases, and its 7 neighbors will each have 1 correct, and it'll be exactly 1 correct because none of the other wrong cases have interfered with it. And this is exactly how we wanted our optimal solution to be. We wanted 112 cases with exactly 1 correct, and we wanted 16 cases with 7 wrong. So when the math gods gives us this set S of k elements, what we will get is basically k cases with 7 wrong and 7 k cases with 1 correct each. Now, if the math gods manage to actually find 16, a set of size 16, that is the optimal strategy. Now, the only question is, can the math gods find us a set of size 16? If the math gods cannot find us a set of size 16, that means that there is no optimal strategy. If they can find a set of size 16, then there is an optimal strategy. Okay, I think so we've already reached the end of the puzzle. Now, all we have to do is answer this maths question. So before we finally answer this maths question, I'm just going to pause a bit for questions from the audience. Okay, so I'm going to just move ahead. Oh,
There's a question in the chat though.
Oh, I see.
So the question, so Rishona is asking if can the above be extended to all odd number of groups?
I was asking in the context of the 3-player solution.
Oh, the 3-player solution. So Janaki gave the strategy for 3 players. And Rishona was asking if that can be extended to all odd number of groups. I guess we'll eventually see.
In the sense, like any group with odd number of members.
Yeah, so we'll see at the end of the. I mean, the answer is not quite, but yeah, we'll see. At least we'll get much closer once we finish the tutorial today.
Now, the math gods do answer us in this case, and what they answer us is they say, look at the Hamming code. So let's just do the Hamming code of length 7. Let's just draw what it looks like. It's very similar to what we saw in the morning. But that's not too wide. So these were special parity bits. This one doesn't even exist. And these were message bits. Now, in the morning, what was said was that if you fill these message bits in any way you want, so you just take any 4 bits to be the message, you take them to be anything, and then you fill the parity bits based on these message bits according to some rule. That is, you want to make all the respective parities have an even number of 1s. Then if you look at, so how many possible ways are there of choosing message bits? There are 4 message bits. So there are 16 ways of choosing the message bits. And the parity bits are decided by the message bits. So that means that there are 16 ways of filling this whole matrix. And what was claimed in the morning, and you actually did see, you solved it yourself, was that if there's any one mistake in this, that is, there are 16 special numbers here, or special matrices, and if there's any one mistake in the matrix, you're able to figure out what the original matrix was. And that is very similar to this diagram over here. These here are the special matrices, what we've written as W cases. If you think of them in the coding term, these are special matrices. And they have the property that if there's one mistake, and that one mistake would take them somewhere here, you're able to tell what the original matrix was. And that is because these two sets don't intersect. These two sets are completely disjoint. This kind of point doesn't exist. So the fact that if there was one mistake, you can find out what the original matrix is. So that is correcting one mistake. This is exactly the same as having distance greater than or equal to 3. That is, between any of these two worst case, the W cases, you need to take 3 steps to go from one W case to another. And what we saw was that distance greater than or equal to 3 was exactly the same as a good hat strategy. The number of things that you can find at distance greater than or equal to 3 would give you a good hat strategy with that many W cases. So correcting one error in coding theory is exactly the same as finding a good hat strategy for our puzzle. And that's crazy. And it's all because of this distance. Distance is a property that comes up in many places in maths, and we'll probably see it again some point. We will see it again at some points in this course. And because it comes up in so many places, if you have figured out how to correct errors well, you can do hat strategies well. And this means that there's probably an alternate universe where people didn't think about correcting errors, but they were thinking about hat strategies. And if they had found out a good hat strategy, then when people started to think about correcting errors, they would have been saying, oh, I know a hat strategy. I'm going to use the hat strategy to find out a code. It's a weird world, but it's possible because distance is the center of it all. And what we saw was that, so the Hamming code actually does give us a set of size 16, which is the same as saying k equal to 4, but I won't try to parse this because I don't have much time. So this sentence I will ignore. So the Hamming code gives us a set S of size 16. It has distance at least 3. So therefore, we get 16 W cases, that is with 7 wrong each. And we get 112 just other cases, which have 1 correct each. And that's how you get an optimal solution to the hat puzzle. Yeah, let's write too much. Yeah, I think I'll stop here for questions. Maybe we'll have a little more discussion at the end if there's time, but I think this is a good place to stop for now. To stop explaining for now, wait for questions and then continue explaining if there's time. I'm not actually stopping. So.
If this was for n is equal to 5, then the distance that should have been maintained is still 3, or?
Yes, the distance should always be 3 for this hat puzzle, and for correcting one error, they're the same thing, and the distance should be at least 3. It is useful to have larger distances, but those would be solving more complicated problems. But yeah. So this also means that if you have n is equal to 15, if there were 15 people participating, then you still use a code which has distance 3 to solve the problem. That's right.
Even in that case, it will cover the entire, like over here, it covered the entire 128.
Yes, so it works whenever it's a Hamming. We know that Hamming codes cover everything. So that is, it works when n is equal to 2 to the k minus 1. 2 to the r minus 1, I think, is what we used in the morning lecture. So whenever n is of this form, then you do have an actual strategy that covers everything. And when n is not of this form, then you don't actually have a perfect strategy. But you can still use codes to analyze what is the best that you can do.
But in that case, the probability will be a bit lesser than.
Yes, it will be slightly lesser. But yeah.
Thank you.
So I think it might be worth pointing out how counterintuitive this is, in the sense that the poll done earlier, there was actually one participant who thought that you could do better than half the cases.
Right. This is, it's quite mind-blowing, which is why this was chosen as the tutorial topic. We can get 112 versus 16, which is ridiculous. So we said that if you have 15, if n was equal to 15 instead, if you have 15 people, then again, your wrong cases would look like 15 wrong, and your right cases would look like 1 correct. So in that case, you would actually have k wrong cases and 15k correct cases. As the number of people keeps increasing, you get better and better strategies. Soon it's extremely unlikely that you'll ever find the wrong case if you take n large enough. Also, it's they say prevention is better than cure. So don't try to get kidnapped. But if you're kidnapped, use the strategy.
So Suhail, should we wrap up because it's 17 past 3? Yeah.
All right. Okay. Sure. So wrap up as in end the stream or finish this slide?
No. You finish. I mean, like maybe take. I mean, like I don't know if you wanted to do something else after this.
I mean, I could have.
I mean, up to you. I mean, I wasn't sure if you were done or not. Yeah.
I see. So how much more time can I take if I do take? I think I should ask the participants rather than the organizers.
Let's not start something new here.
Yeah, it won't be starting something new. It will just be musings. Okay, so I'll tell you at least what patterns I hit. So there are similar hat problems that you can still solve with using codes. So this is one particularly simple one where you don't allow the players to pass. They always have to guess. Every player always guesses. So we saw that you can win half of the cases if the first person guesses and everybody else passes. That's one thing that we saw. And the question here is, suppose nobody is allowed to pass, can you still win half of the cases? I'll tell you the answer is yes. And you can think of this in terms of distance. And then from that, you can actually go back to codes, and something you saw in the morning will actually give you the answer, which tells you how to win half the cases. Another question is, I know distance is such a useful quantity, then are there other mathematical objects that we can think of that are distant from each other? If we can find such mathematical objects, maybe some that we're already familiar with, we can use them to create codes, and it enriches the very and almost everything. I think somebody said that they pop up in so many roads because they have codes. Yeah, that is true. I think so. Tomorrow, I believe you will be seeing some other mathematical objects which we're already familiar with and that are known to be distant from each other. And so we should definitely attempt. Very cool stuff. Yeah, that's it, I guess. I mean, if someone wants to see scary looking diagrams. So I tried to draw a diagram of basically this. So it looks scary enough when there are only 2 wrong cases. I tried to draw it with all cases being shown. It's a little scary, but I think I can share it. Yeah, so this is what the whole thing looks like. Okay, no. Yes. So here are the 128 different cases, and each case is connected to another case if they differ in just one hat color. And I thought it would look nice, but in hindsight, yeah, it probably is going to look complicated. It's like a 7-dimensional object that we've just flattened onto a 2-dimensional paper. And this is what it looks like if you take the dots. So these are all the things in green are all the W cases or all the code words. And I've drawn how they connect. So these are all the things that are distance 1 from the code words. And if you have really good eyesight, you can see that none of these balls actually intersect with each other. And they actually cover every single element out of the 128 elements. All right, I think I'll stop with that.